Okay, I want to talk about the rational functions, what we've been doing in 153 for section 3.7. First of all, we did a lab and we collected some data. And I've taken the lab data from one student's lab, and you were supposed to graph it and then come up with an equation. And I gave this as a model to start talking about it. And I'm using my computer, so the screen's kind of crazy here, but hopefully we can get through this with this. All right, so y equals 1 over x makes this kind of curve. Because if you put 1 in for x, 1 over 1 is 1. And if you put 2 in for x, you get 1 over 2, or a half. 1 over 3 is a third. 1 over 4 is a fourth. 1 over a half is 2. 1 over a quarter is 4. 1 over a fifth is 5, and so on. So it makes this curve, and it does a similar curve for the negatives you can see over here. And just like any equation, what we've learned before is that you can move these around, and we can change the shape. So I'm going to put first a minus b there, and let b be a slider, and you can see then that I can slide it sideways. Okay? Either positive or negative, because it's working on the x. And I can put something here in the numerator like a and make it a slider, and you can see what that does. As it gets bigger, it moves it further away from the origin. Smaller, it gets closer. If it goes negative, it flips it in that direction. Okay, I've graphed the data. Now, if you don't know how to do that, you can just click on like an equation. I'll go down here and do one. I'll just type in x. Then I'll type the wheel, and then I can make a table from that, and I can get rid of my x, get rid of that, or leave it on, but change it to to a y, and then I can just type in my values for x and y, and it'll plot them. So I'm going to get rid of that and this, and I've plotted the data here, and it's over here, and it's spread out. So I'm going to zoom out so you can see it. And it has a curve shape. And that curve shape is similar to what 1 over x is adjusted with the a and b. Now, with a being positive, it goes in the wrong direction. But when a is negative, it's kind of in the right direction, but it needs to be moved to the right and adjusted in shape. Now, I needed to go further than what it's doing, so I'm going to go on here and make it go from minus 100 to 0. I don't need to do the positives. Oh, and I'll make the steps 1. Okay, so now I can slide it, and it can bend it more, clear to minus 100 up to 0. Okay? But I need to move it over. So I'm going to move it over by sliding the B. It looks like I need to go further than that. So that's at 10. So if I click on that, I can go 0 to, say, 50. Step 1. So now I can move it over farther. I can change the shape and move it over, and I can get a graph that's approximating our data. And that's what you were supposed to do in the lab. You notice that this is avoiding right now 21, where it's what's in the denominator. X minus 21 is what's going on, and it completely avoids 21. I'll show that by typing in x equals 21. And you see how this curve avoids that line. This line that the curve gets closer and closer and closer to, but never touches, is called an asymptote. Let me type that in here so you know how to spell it. A-S-Y-M-P-T-O-T-E. An asymptote is a line that the curve gets closer and closer and closer to, but never touches. Vertical ones. Horizontal ones, this has a horizontal asymptote of the x-axis, or y equals 0. Let me type that one in. And you can see that it's there. If I change it, I'm moving that around, but if I just leave it at 0, that's what this graph, let's go zoom out. Do you see how it gets closer and closer and closer to 0? Not to 10 or minus 10, it gets closer and closer to 0. We're going to learn more about that as I go along here, but it has a vertical asymptote at what would make the denominator be 0. And since b is 21, x minus 21, it has an asymptote at 21. So the whole lab that I did was to get used to seeing places where we get this kind of curve. 3 of the 4 labs have a curve that comes from something over x, and the x could be plus or minus something. One of them is just a linear one. Okay? All right. I'm going to get rid of all of what we've done here now, and we're going to start exploring what happens when we put different things in the denominator. So I'm going to have y equals, and I'm just going to put 1 divided by x minus 2. And let's get in here close so we can see what's going on here. And do you see that we have a vertical asymptote at 2? This graph at all costs avoids 2. You cannot let x be 2 because that would be division by 0. When it gets close to 2, like 1.9, you get 1.9 minus 1, which is minus 2, which is 0.1, and 0.1 into 1 is 10. So at 0.1, it's clear down here at minus 10 at 0.1. So if I put in 1.9, I'll get minus 10. If I put 2.1, minus 2 would be 1 divided by 0.1, which would be at plus 10. And that's exactly what's going on here. The closer I get to 2, the closer this denominator becomes 0, and the more times it will divide into 1, and so it gets bigger and bigger and bigger, either positive or negative, going off to negative infinity or positive infinity, but it gets closer and closer to 0. So it avoids 2 completely. It heads off to infinity or negative infinity. There's a reason why it goes closer and closer to 0 horizontally, and we'll get to that. Now, notice what happens if I take this factor in the denominator and change that factor's multiplicity to 2. Before the graph, one of them went down and one went up. That's because when we were below 2, like 1.9, this was a negative number, and divided and positive made it negative. But now that we square it, there is no negatives coming out of it, and it's all going to the positive infinity. If I put a negative on the numerator, that just flips the whole thing over, and it goes to negative infinity. So If I go to 3, now they're back to going in opposite directions. Whether it's positive or negative, they go in opposite directions. If I go to 4, they go in the same direction. If I go to 5, it changes shape a little bit, but if it's an odd power, they're going to go in opposite directions, and if it's an even power, they go in the same direction. Okay? Now, I'll leave that with the 2, and I'm going to go put another factor down here, like x plus 3. Oop, and I didn't put plus. Now, let's back off a little bit. You notice that it's avoiding 2 right there. It's also avoiding negative 3. Well, negative 3 plus 3 would be 0, and it can't divide by 0. So we got 2 vertical asymptotes now. This one, because of the multiplicity being 2, we have it going in the same direction, getting asymptotically closer to 2 in the same direction, and at the minus 3, it's going in opposite directions. And so forth. I could keep adding factors here and getting more and more asymptotes, and if I change the multiplicity on this one, let's say squared, then they would both go in the same direction. And so I'll just get rid of that. Okay, so now get rid of that power. Come on. Right there. Okay, so there we have this. What happens if we put a factor in the numerator? Like x minus 1. Well, if I do that, you notice that this graph now has an x-intercept of plus 1. If I put plus 1 in for the x, we get 1 minus 1, or 0, over stuff. If I put the 1's in there and I get a number, but I get 0 over a number, which is 0. Anytime I have a fraction, which is what I'm dealing with here, a rational function, a ratio of two functions, if the numerator is 0, the graph has an x-intercept. And just like what we had in the last section, if the intercept has a multiplicity 2, it doesn't cross, but it bounces. If it was 3, it would come down, hesitate, and then go on down. If it was 1, it goes more straight through, and it's hard to see the difference between a 1 and a 3. But that's what's going on. So right now, it has only 1. Now I want to show you something else with the 3. No longer does this graph go to 0 on the ends. I'm going to back out. Do you see how this graph now approaches a height here, and that height is y equal 1. See how it's getting closer and closer to 1. And I will explain how we know that coming up here. But so far, we've got zeros happening from the numerator and vertical asymptotes happening from the denominator. That's the main thing up till now that I want you to get. And I can put more intercepts, x-intercepts. Let's try just x. So now if I get in close here and look at this, I should see that it crosses at 1. That's a low spot, but it crosses again at 0. because 0 would make the numerator 0, and 1 in this would make it 0. And so I have two x-intercepts. I could make it have an x-intercept at 4 by putting parenthesis, well, let's just go back in here and put in minus 4. And notice now it has an x-intercept at 4 and at the 1. I could make it come up and bounce off of 4 and then go down by squaring that factor. So now it bounces. Still goes through 1, and it bounces at 4. Okay? So, understand how to read this for x-intercepts and for vertical asymptotes. Okay. Now, let's see. What do we want to talk about next? Let's talk next about this in behavior. So if I back out, notice this one is approaching a height of y equal 1. Okay. If this numerator were multiplied out, what would be the degree? Well, we'd have x times x times x twice. So we'd have x to the third. So the degree of the numerator is x to the third. The leading number would be 1x to the third. Okay, 1x to the third. If the leading coefficient on the denominator, let's see, we'd have x twice, so x times x times x. That's 1x to the third. And it's the strongest term that controls what happens. Well, the x to the thirds would cancel. There'd be some other stuff that wouldn't cancel, but the ratio of the leading coefficients tells us what the horizontal asymptote is. And that would be 1 on this. Now, if there happened to be a 3 here, like 3x minus 1, then it would go through 1/3 on the graph. Let's zoom in to see that. You see how it's going through 1/3? And now let's go back out, and you can see how it's not approaching 1 anymore. It's approaching 3. And that's because now when I multiplied the numerator together, I would get 3x to the third, and the denominator would still have 1, and so 3 over 1 is 3. And so that's the horizontal asymptote. That works if the degrees are the same. If the degree of the numerator is less than the denominator, so I'm going to take the 2 out. Now the degree of the numerator is 2. The degree of the denominator is x to the third, and even though this would be 3x squared, and this is 1x to the third, doesn't matter what these numbers are now. It's because the denominator is a higher degree. This is going to grow faster than the numerator, and this whole thing is going to go towards 0 when x gets really, really large. So when x gets really, really large, out here, further and further, it's going to go towards 0. I'm going to look closer at this, even closer. And you see how this has gone up? But as we move out, it's going to get closer and closer and closer to 0. And same with the other side. So whenever the degree of the numerator is less than the denominator, the horizontal asymptote will be 0. If they're equal degrees, the horizontal asymptote will be the ratio of the leading coefficient, be it 3 over 1 or 2 over 3 or whatever the numbers are in front of the equal powers, the big equal powers. That's what will be the horizontal asymptote. Now, what happens if the numerator gets to be a higher degree than the denominator? So I'm going to, I'll just square this one. I'll cube that one actually, to the third. Now let's take a look at this graph. And let's get rid of this line and zoom out. And we have it approaching a slanty line. It's called an oblique asymptote. O-B-L-I-Q-U-E. Oblique asymptote. It's a y equals mx plus b, a line. And we're going to try to figure out what that line is. Now for this one, it's messy. So I'm not going to do that one. I'm going to do a simpler one. I'm going to reduce this to, let's see, let's just take and make this 2, get rid of this, and make this be just x minus 3. Do you see the oblique asymptote there? To find that equation, we need to do synthetic division or long division. So here we go. It's x minus 4 in the numerator squared. So to do that, I'm going to multiply this out, and that would be x squared minus 8x plus 16. That's taking x minus 4 times x minus 4. X squared minus 4x plus 16. And I got to divide it by my denominator, which is x plus 3. And if I do that, x goes into x squared, x times x is x squared, x times 3 is 3x. Draw the line, change the sign, add the like things, and I get negative 11x plus 16. X into there would be negative 11. Negative 11x minus or plus 33. Draw the line, change the signs. It becomes 0 and minus 17. So I'd have minus 17 over x plus 3. We've done that before. This part, if x gets really large, the denominator of this remainder would get large, and this part would go to 0. Play that back if you didn't catch that. If x gets large, x plus 3 gets large, and 17 divided by a large number is close to 0, and so we get just this, y equals 11 minus x. Let's go to that. Y equals 11 minus x minus 11, excuse me, said it wrong, x minus 11. Do you see how this graph gets closer and closer to that slant or oblique asymptote? So you divide the denominator into the numerator. If this is a simple factor like this, you could actually do it with synthetic division. Let me show you that. So we would have had x squared minus 8x plus 16 divided by x plus 3. So synthetic division, we'd have 1, negative 8, 16, minus 3 makes that 0. 1 plus 0 is 1, times minus 3 is minus 3. Add, we get negative 11, times minus 3 is plus 33, and we get 49. We don't care about that. This was x squared. It becomes y equals 1x minus 11. Got the oblique asymptote. Sometimes you have to do long division. Sometimes you can do synthetic division. But that's how you find this oblique asymptote. All right. Now, let's do one more thing here. Let's make it just not an oblique asymptote. And let's get rid of that. And let's put in, down here in the denominator, x minus 1. And let's get closer to it. So, if I put x minus 1, there's an asymptote at plus 1. A vertical asymptote. If it's got x plus 3, there's a vertical asymptote at x minus 3. And if I wanted to go in the same direction at the plus 1, I would square it. So I can go here and put a square on that. Now they both go in the same direction there. If I wanted to touch at, let's say I wanted to bounce off, it's going through at 4 because of that. Let's say I wanted to go touch at 1, minus 1. I would change this to plus 1. And now it goes through plus 1, or minus 1. Because minus 1 plus 1 would be 0. Okay, and it doesn't go through 4 anymore. Okay, that's the kind of stuff we're going to be playing with in class. And then you could adjust. For instance, right now it has a y-intercept of pretty small. If I wanted to get up here at 1, I might have to multiply it by 3 to stretch it up a little bit. Okay. Now, right now, there is a vertical asymptote at minus 3 because of this x plus 3. I'm going to go up here and go parenthesis x plus 3. Oop. Plus 3. This says there should be a vertical asymptote at negative 3. This says there should be a x-intercept at negative 3. Well, we see neither of those. What has happened? Well, you can see that those would probably cancel out in this problem. But what's going on in the graph? So I'm going to put my cursor on this, and I'm going to go follow the line to negative 3. And this is not doing what I expected. Let's see, what did I do wrong here? x plus 3, x plus 3. It should be at minus 3. No. Something's wrong here. Okay, I'm going to hit the gear. I'm going to do table. And at minus 3, it says it's undefined. That's what it should have done. If I follow this with the cursor at minus 3, it should give me no value. I don't know how it's coming up with this number. It's doing something incorrectly. But there should be no value because x plus 3 and x plus 3, I cannot put a minus 3 into this equation it gives me division by 0, which is undefined. But you don't see an asymptote, and you don't see a 0, an x-intercept, there either. That means there's a hole there in the graph. I'm not sure why it's not showing it, but it should show a hole there. Now, if I put, and that's because these cancel. And if they cancel, this equation would look like y equal, and in the numerator it's 3 parenthesis x plus 1 close parenthesis, and in the denominator it would be parenthesis x minus 1 close parenthesis squared. Now, let's change the color of this so you can see the difference. So there's the red. There's, turn that one off, and there's the black. Let's zoom out a little bit so we can see more of this. Turn the red one on, turn it off. It looks like identical graphs. The difference is this one I can put minus 3 into it, and the top one I can't. This one I can. So if I want to know the value that is supposed to happen at minus 3, let's see if I follow this now. It's still saying that, and it shouldn't. It should say undefined. When I did the table, you saw it was undefined. This one would have it defined. What does it come up with for this? Oop, undo that. Table, and at minus 3, it's negative 3.75 on the red one. But on this one, it's not supposed to be there. So there's a hole in the graph. When there's a matching factor in the numerator and denominator, it causes a hole. So this graph has a hole at minus 3 and negative 3.75. The graph that I drew here is almost the same as this one. This one does not have the hole, and this one up atop here does have. The black one has a hole. The red one does not have a hole. Those factors cancel. Now what happens if I make this factor happen more, like squared? Notice that asymptote happens again. That's because the x plus 3 would cancel one of those and still leave an x plus 3 in the denominator, which would cause there to be an asymptote. Okay, so we have 4 things that I'm trying to get you to see about these. Number 1, vertical asymptotes happen when the factors in the denominator are 0. X-intercepts happen when the numerators are 0. And the multiplicity of the factors in the denominator cause behavior to either go in the same direction by the asymptote or in opposite directions by the asymptote, depending on whether they're squared or not. Okay, let's see, this is at minus 3, so this was without that. Excuse me. Let's take this out so we'd see that. So we have one there. This is going opposite, and this is going the same direction. If I put a square on that, they both go in the same direction. The numerator gives me x-intercepts. If it's squared, it's going to bounce at that x-intercept. If it's to the cubed, it's going to come down and hesitate. So the same stuff that we had from the polynomials in the last section. So the multiplicity of the factors is important to be aware of. Third thing that we talked about If the degree of the numerator and the degree of the denominator are the same, then it's going to approach a line that's equal to the leading coefficients. Here, the degree of the numerator is 2. It's going to be x squared. It's going to be 3x squared. The denominator is going to be x to the 4th. When the degree of the denominator is bigger than the numerator, it's going to have in behavior heading towards y equals 0. If they are equal degree, let's take this out of here. Equal degree, then they will go to the ratio of the coefficients. In this case, 3 over 1, because I'm going to have 3x squared over 1x squared. So this will approach a horizontal line of 3. And if the degree of the numerator is 1 more than the denominator, it'll approach a slanty line that you get by either synthetic division or long division to figure out the equation of that oblique or slant line asymptote. Okay? Those are the main things that we've learned up till now in 153 about rational functions.